Hello, so my name is Saliha Kaisi. I am one of the Advanced Optical Imaging Group member. I work in retinal imaging. This is my system here. But before I explain my work, I want to explain and talk a little bit about the basic of image formation on the eye. So we will start with that part first. So here we see a very basic eye model capturing the light reflected from an object, which is a tree in this case, and the image is formed upside down at the back of the retina. The reflected light of the tree goes to the eye through the iris, to the cornea, which is a thin glass not seen here, to the lens, forming an image at this white plastic part representing the retina. The upside down position of the image is then corrected by the neuroprocessing of our brains. Here we see a diagram of what I've just explained, and if we send an intensive light to the eye, some of the light would be reflected back. You could see this sometimes as a scary red eye effects when you capture images with a flashlight. If we capture this light with a camera, then we will get images of our retinas, and that's what the optician does when you go to check your eyes. There are more advanced retinal imaging techniques. One of them is adaptive optics, and as you can see, the system started to get a little bit complicated with more optics components added. The two mains are the wavefront sensor and the adaptive elements. The wavefront sensor measures the aberrations of our eye, send the signal to the adaptive elements, which is capable of deforming its shape to correct for the aberrations. When we correct the aberrations, we capture higher resolution images that enable us to resolve the cellular structure of the retina as the cone photoreceptors in this picture. My PhD work was to build a differential adaptive optics retinal imaging system where we simultaneously capture 4 different images. And then with numerical analysis, we were able to determine the directional scattering of the retinal structure. You can see this for the cones here. And we image the blood vessel as well as the optic disc. This technique is potentially useful on the diagnosis of diseases that alter the topography of our retinas and in studying the structure of the retina in general. Thanks for listening. You will hear more about the retina in a coming talk, and I hope you have a nice day at the festival. Thank you.
Hello, my name is Brian Wohnsen, and in my research I try to understand exactly how light interacts with photoreceptors in our retinas. The retina is a thin layer, a fraction of a millimeter thick, covering approximately 70% at the back of our eye, and the light of the outside world is projected upside down onto the retina, much like in a pinhole camera. The central region of our visual field, called the fovea, is located right in the middle of what we also know as the macula. You see it here as this darker region in a fundus image. And there are hardly any blood vessels in this region. We call it the avascular zone, whereas in the rest of the retina, we have plenty of blood supply. All of the nerves, all of the blood goes through the optic nerve here, which is basically what connects to the visual cortex and the brain and gives us the sensation of vision. The photoreceptors are very elongated cells, and light travels the entire length to the outer segments where vision is triggered. We have about 90 million rods and just 6 million cones in each eye, and in the central fovea we only have cones providing us with daylight vision. Diseases, unhealthy lifestyle, and even just age can lead to modification in the retina that result in vision loss and even blindness. Age-related macular degeneration affects up to 10% of people aged 55 years or more, and it can result in fluid that builds up in the retina or small hard drusen, also seen here in cross-section, small bumps in the retina, where basically the photoreceptors are being pushed away from the rest of the layers in the retina, and thereby at some point people lose central vision, creating this kind of dark spot in the center of their visual fields. So an effect of special interest to me is known as the Stiles-Crawford effect that was discovered 89 years ago. It's still not fully understood, although I think we are closer than ever. The outer segments in the photoreceptors contain visual pigments in about 1,000 layers, and these pigments are gradually renewed in roughly a 10-day cycle. Essentially, we can consider the outer segments like layers of pancakes with visual pigments then embedded inside of each layer. Now, if we change the direction of incidence of light onto the retina, we have what is known as the Stiles-Crawford effect, and this is similar to the phototropism we see in sunflowers that are also in Latin called girasol, meaning turning towards the sun, and basically the retina itself has plasticity and is able to adapt to changes in illumination conditions.
Hi, this is Nazneen, and I'm working mainly on accommodation of the human eye. This is the optical system I built, and so what is accommodation of the eye? Our human eye can focus at different distances from near to far or far to near by altering the shape of the lens. So this process is known as accommodation of the human eye, and in this setup what we are trying to do, we have a tunable lens in the system where with what we create defocus in the system, and the subject actually sit here biting on the viva. Then we induce the defocus on the lens, and the subject's eye itself correct the defocus, and the response we are capturing by this Harman-Shake wavefront sensor. And so this may sound a bit complicated, but I will describe in a simpler way what is really the idea of accommodation. As you can see, this is an eye model, and so this thing actually, it replicates, as you can see here, this replicates our lens inside the eye, and as you can see, just by pumping, I am changing here the shape of the lens. So that's what happened during the accommodation process. So our human eye lens actually can change the shape, and just to show it better, if I put the lens inside, and by changing the lens, as you can see, if the image is out of focus, then by changing the lens I can bring the image into focus. Now you can see a clear tree, and now again out of focus, and again we can bring it into focus. So this is the process actually which called accommodation of the eye.
When a person is looking at a far object, then the eye is actually in relaxed state. Then the lens is thin and long like that. You can also see here, and in that case the zonular fibers are under tension, but the ciliary muscles are also relaxed in the relaxed state. On the other hand, when the person is looking at a near object, let's say for reading or looking into our phone, then the eye is actually in accommodative state. Then the lens become thick and short like that, and you can see here as well. And in that case the zonular fibers are relaxed actually, but the ciliary muscles are in contract with the lens itself. So it is a well-known fact that for the accommodation process the ciliary muscles actually plays very important role.
Before starting the actual measurements, we aligned the subject with the system. With the right eye, the subject kept looking on the target, and their left eye is covered with the patch. And we saved the real-time measurements where we can see the accommodation response live as well.
Hello, welcome to UCD Festival. Have you ever heard terahertz? Do you want to know what is terahertz? Firstly, 1 terahertz is equal to 10 to the power of 12 hertz, and 1 gigahertz is equal to 10 to the power of 9 hertz. Terahertz is an electromagnetic wave which has a frequency from 0.1 to 10 terahertz. As a comparison, the frequency of visible light is over 400 terahertz, and the frequency of microwave is less than 30 gigahertz. Unlike visible light, for example, this is a green light, and red light or yellow light, terahertz is invisible. the terahertz source is on now. We can't see terahertz radiation, but we can see the terahertz radiation on the terahertz camera. Terahertz can penetrate many materials such as clothes, plastics, and some biomedical samples. For example, this is a sponge. We put this in a terahertz path, we can still see a very strong radiation. And this is a clothes, a mask. We put this on the top, in front of the camera. You can see this strong radiation. And this is a plastic, black plastic. There's a T-shaped metal strips on the top. If we put this on the top of the camera, we can see a clearly T-shape on the screen. So are terahertz dangerous like X-rays? The answer is no. Low intensity terahertz pulses are believed to harmless for living organisms. What is terahertz used for? So as we know, terahertz is harmless and has strong penetration abilities. So it has a great promise for security and medical imaging applications. Also, terahertz frequencies is useful for spectroscopy in various areas, such as investigation of superconductive, plasmonic effects in conducting materials, and rotational states in molecules. This is because the fundamental resonance of these materials are in terahertz region. Thank you.
Hello guys, welcome to UCD Festival. Today I'm going to introduce a little about optical fiber. First of all, what is optical fiber? The optical fiber is a fiber made of glass or plastic that can be used as a light transmission tool. The system used optical fiber to transmit the light waves, and the light waves could carry the information to achieve the purpose of communication. The principle of the optical fiber is total internal reflection. So the light could bounce inside the optical fibers to achieve the light transmission. Now let's see some examples. This is a group of fibers. We can see the two ends of the group fibers. If we put a light source to one side, although the fiber is not straight, we can still see the light signal in the other side. If we change to another light source, it's the same effect. This is a kind of fiber with a beam splitter inside. We can see the change of the light. The easiest product is a light decoration. Can you find any fiber products in your life?
Dear UCD Festival visitors, my project is to build up a system to measure the wavefront aberration of human eye. The core element we use is the Hartmann-Schick wavefront sensor. The sensor captures the reflected light from the eye. The wavefront aberrations of the eye can be calculated from the spot distribution. Our barometers can measure the refraction of your eye and is widely used for evaluation before and after eye surgery.